On October 4th, 2025, a photo from Mars changed everything. The Perseverance rover captured something in the Martian sky. Not a dot, not a smudge, an elongated, glowing object 4 times longer than it is wide. And the internet absolutely lost its mind. Within hours, 2 camps emerged. On one side, Harvard's Avi Loeb explaining it away as a simple camera trick, stacked images creating an illusion. On the other, Dr. Horace Drew, a scientist who worked at Caltech in Cambridge, saying the math doesn't work, that if there's a green nickel coma surrounding this thing, the center should be green too. But it's not. It's white. But here's where it gets really strange. NASA went silent. Then ESA. Then China, who always releases Mars images for propaganda. Then the UAE. 4 competing space agencies, rivals on the world stage, all refusing to show us what their Mars orbiters saw during the closest flyby in history. The timing. NASA's government shutdown started October 1st, exactly 48 hours before the flyby. Convenient. And now, as 3I Atlas races toward the Sun, approaching perihelion on October 29th, we're facing 2 possibilities. Either this is the most unusual comet ever discovered, pumping out industrial-grade nickel alloys and defying every natural explanation we have, or something far more extraordinary is happening above Mars. In this video, we're going to break down the evidence both sides don't want you to see, the photos, the silence, the anomalies, and why October 29th might be the day everything changes. If you're as fascinated by this as I am, hit that like button and subscribe to stay updated. And tell me in the comments where you're listening from, what time it is there, and which explanation you find more convincing, the camera artifact or something else entirely. And if you want to help our community grow, share this on X, Facebook, Reddit, or your messenger. Thank you for always having our back. Chapter 1. The photos that changed everything. Let's start at the beginning, or at least what feels like the beginning for most of us. October 4th, 2025. A date that will either go down in history as a turning point in human understanding, or as yet another moment when we got carried away with speculation. The verdict is still out, and that's precisely what makes this so compelling. The Perseverance rover, sitting in Jezero crater on Mars, had been tasked with something unusual. For days, engineers back on Earth had been preparing for this moment. The 3rd confirmed interstellar object ever detected, designated 3I Atlas, was making its closest approach to Mars, 38 million kilometers away, but in cosmic terms, practically a handshake. This was humanity's best chance to get a good look at something that came from beyond our solar system. From the vast darkness between stars where we've never sent a probe, never captured an image, never truly understood what might be out there. The rover's right navigation camera, or NavCam, began its sequence. These aren't the fancy color cameras that give us those stunning panoramas of the Martian surface. The NavCam is more utilitarian, designed to help the rover navigate, to avoid obstacles, to plot its route across the rusty terrain. It captures images in black and white with an angular resolution of 33 milliradians per pixel. Technical specifications that mean very little until you understand what they translate to. At 38 million kilometers, about 12,500 kilometers per pixel. Think about that for a moment. Each pixel in the image represents an area larger than Earth's diameter. You're not going to see fine details. You're not going to count windows on a spacecraft or read serial numbers. But you should be able to see the rough shape of something, especially if multiple images are combined to reduce noise and increase the signal. And that's exactly what happened. The Perseverance team, or perhaps more accurately, amateur astrophotographers monitoring the raw image feeds, began stacking the NavCam frames, Not just 2 or 3 images, but hundreds of them taken over approximately 10 minutes of Martian time. The stacking process is common in astrophotography. When you're trying to capture something faint, you combine multiple exposures. Random noise averages out, but real signals add up. It's how amateur astronomers capture nebulae with backyard telescopes, how professionals tease out the faintest galaxies at the edge of the observable universe. When those images were stacked, something appeared. Not a circular dot, not a fuzzy blob with a tail streaming behind it like every comet we've ever seen from Earth. No, what appeared was a stripe, an elongated feature roughly 4 times longer than it was wide, glowing against the background stars. And critically, it appeared white in the center, with hints of green around the edges. The image spread across social media within hours. Reddit threads exploded with hundreds of comments. X, formerly Twitter, lit up with amateur astronomers, conspiracy theorists, professional scientists, and everyone in between weighing in. YouTube channels rushed to analyze the pixels, to enhance the contrast, to draw conclusions. And at the center of it all was a question that seemed simple, but carried enormous weight. What are we actually looking at? The mainstream explanation came quickly. Avi Loeb, a professor of astrophysics at Harvard and director of the Galileo Project, had been following 3I Atlas since its discovery back in July. He'd already published papers suggesting the object displayed unusual properties, anomalies that didn't quite fit the profile of a typical comet. But when the Perseverance image went viral with people asking if it showed a cylindrical spacecraft, Loeb took to his blog to explain what he believed was happening. The elongation, he wrote, was an artifact, not of alien technology, but of simple physics and how cameras work when objects are moving. 3I Atlas was traveling at about 67 kilometers per second, relative to the Sun in a retrograde orbit, opposite to the direction Mars moves. From Mars's perspective, the object was screaming across the sky. Over 10 minutes, it would travel roughly 50,000 kilometers. If you're stacking hundreds of individual frames taken over that time period, you're essentially creating a time lapse. The object's motion gets smeared across the final image, creating the illusion of elongation. It's like photographing a car driving past at night with a long exposure. The car itself might be compact, but in the photo, it appears as a streak of light stretched across the frame. The headlights and taillights leave trails. You wouldn't conclude the car is shaped like a ribbon just because the photo shows it that way. Loeb calculated the numbers carefully. The navcam's angular resolution meant each pixel covered 12,500 kilometers at 3I Atlas's distance. The stripe appeared about 50,000 kilometers long. Divide that by the object's velocity relative to Mars, roughly 91 kilometers per second when you account for both their motions, and you get approximately 9 to 10 minutes, which matched the integration time needed to stack enough frames to bring the faint object above the noise threshold. The math checked out. The explanation was elegant, straightforward, grounded in well-understood principles of imaging and motion. Case closed, right? Not according to everyone. Dr. Horace Drew, who goes by the online handle Red Collie, is not someone easily dismissed. His credentials include work at Caltech and the MRC Laboratory of Molecular Biology in Cambridge. He's published research on DNA, crop circles, and what he describes as extraterrestrial computer codes. To some, he's a maverick willing to explore ideas the mainstream rejects. To others, he's ventured too far into speculation. But his counterargument to Loeb's explanation raised eyebrows because it focused on something observable in the images themselves. Drew pointed out that the enhanced color versions of the stacked images showed something crucial. The center of the stripe appeared white, while the edges showed a greenish tinge. This, he argued, was consistent with observations of 3I Atlas from Earth-based telescopes showing a green, nickel-rich coma, a cloud of gas surrounding the nucleus. If the elongation was purely an artifact of stacking images of a small, rocky ball moving through a larger green coma, then combining those frames sideways should result in the central stripe appearing predominantly green. There would be so much accumulated green from the coma in each frame that the final stacked image couldn't possibly maintain a bright white center. Unless, Drew suggested, the object itself has an extended white shape, an exile structure, as he described it, that is significantly larger than the green coma around it. In that case, stacking the images would preserve the white dominance in the center, because there's simply more white material than green in each individual frame. It's a geometric argument about ratios and how colors combine when you stack images. And it's not easy to dismiss without detailed modeling of what the coma's extent and brightness would be at that distance, how it would appear in NavCam's black and white captures that were later colorized, and what the actual nucleus size and shape might be. Drew also emphasized that multiple Mars orbiters from different countries had taken photos during the flyby. The Mars Reconnaissance Orbiter, Mars Express, ExoMars Trace Gas Orbiter, China's Tianwen-1, the UAE's Hope probe. All of them pointed instruments at 3I Atlas during its closest approach on October 3rd, and yet, as of October 6th, when Drew and others were posting their analyses, not a single official processed image had been released by any space agency. The raw Perseverance NavCam frames were publicly available because NASA posted them automatically. But the high-resolution images from HiRISE, the camera aboard Mars Reconnaissance Orbiter, capable of 30 kilometers per pixel resolution at 3I Atlas's distance, remained unreleased. The spectroscopic data that could reveal the chemical composition of the coma, the color images from CASIS on ExoMars, the infrared observations from HOPE, all of it stayed behind closed doors. Why the silence? NASA's answer was straightforward. The United States government had entered a shutdown on October 1st, 2 days before the flyby. Thousands of NASA employees were furloughed. Websites weren't being updated. Press releases weren't being drafted. The agency, in its own words, was operating with minimal staff focused only on mission-critical activities. Processing and releasing images of an interstellar comet, no matter how scientifically interesting, apparently didn't qualify as mission-critical during a funding lapse. But the timing struck many as suspicious. A shutdown beginning precisely 48 hours before the most anticipated astronomical event in years. It felt almost too convenient, and it didn't explain why ESA, the European Space Agency, operating independently of American budget politics, also remained silent. Or why China, which routinely releases images from its Mars missions as a matter of national pride and to showcase its space program's capabilities, had shared nothing. Or why the UAE, eager to demonstrate the success of its Hope Mars mission, the first Arab interplanetary probe, hadn't jumped at the chance to show the world what their instruments captured. This wasn't just one agency dragging its feet. This was coordinated silence across geopolitical rivals, nations that compete for prestige, funding, and influence in space exploration. And that silence, more than any single photograph, became the story. Because in the absence of official data, speculation rushed in to fill the void, and with 3I Atlas, there was already plenty to speculate about. Chapter 2. 2 options, 1 truth. The debate crystallized into something resembling a scientific duel, played out not in peer-reviewed journals with their months-long review processes, but in real time across blogs, social media platforms, and hastily organized video conferences. This wasn't how astronomy typically worked. Usually, observations are made, data is carefully analyzed, papers are written, submitted, revised, and eventually published. The process takes time, patience. Peer review ensures that errors are caught, that alternative explanations are considered, that conclusions are supported by evidence. But 3i Atlas didn't allow for that luxury. It was moving. Every day it traveled millions of kilometers closer to October 29th. After that, it would swing around and begin its journey back out of the solar system, accelerating as it fell away from the sun's gravity well, eventually leaving our celestial neighborhood forever. The window to observe it, to gather data, to understand what it truly was, that window was closing. And so, the debate happened in fast forward, with scientists, amateur astronomers, and interested observers all weighing in simultaneously. The core question seemed deceptively simple. Was the elongated appearance in the Perseverance images a real physical characteristic of 3i Atlas? Or was it an optical illusion created by how the images were captured and processed? To understand why this matters, you need to grasp what each answer implies. If it's a camera artifact, then 3i Atlas is likely a relatively compact object, perhaps a few kilometers across, surrounded by a diffuse coma of gas and dust. Unusual, certainly, given its interstellar origin and chemical composition, but fundamentally a comet. Strange chemistry, yes. Odd trajectory, absolutely. But still a natural object formed in another star system billions of years ago, ejected by gravitational interactions, and now passing through our solar system by chance. If it's not an artifact, if the object genuinely possesses an elongated structure, then the conversation shifts dramatically. Natural objects in space tend towards certain shapes. Small bodies are irregular like asteroids because their gravity isn't strong enough to pull them into spheres. Larger bodies become spherical or oblate spheroids if they're spinning fast. Elongation ratios of 4:1 are rare for natural objects. Not impossible, but requiring specific formation scenarios or structural compositions that can support such shapes against gravitational collapse or tidal forces. An elongated structure immediately invites comparison to ʻOumuamua, the first confirmed interstellar object discovered in 2017. ʻOumuamua was also elongated, estimated at roughly 10:1 based on how its brightness varied as it tumbled through space. That elongation sparked endless debate. Some argued it was a cigar-shaped asteroid. Others suggested it might be a flat disk seen edge-on, like a pancake. And Avi Loeb himself had proposed controversially that it could be a light sail, a thin, artificial structure designed to be pushed by starlight. Oumuamua's elongation combined with its non-gravitational acceleration as it left the solar system, acceleration that couldn't be fully explained by outgassing like a normal comet, made it anomalous. The scientific community largely settled on exotic but natural explanations. Outgassing of hydrogen that wouldn't be visible or solid nitrogen ice, sublimating in unusual ways. But the debate never fully resolved, and Loeb continued to argue that artificial origins shouldn't be dismissed without evidence. Now here was 3i Atlas potentially showing elongation again. If real, it would be the second highly elongated interstellar object out of only 3 ever detected. That's a pattern. 2 out of 3 is 67%. If elongated shapes are rare among natural objects, but common among interstellar visitors, you're forced to ask why. What makes interstellar objects different? Are we seeing selection effects where only certain shapes survive ejection from their home systems and the journey through interstellar space? Or are we looking at something else entirely? The mathematical arguments became intricate. Several astrophysicists who weren't directly involved in the Loeb versus Drew exchange started running their own simulations. If you model 3I Atlas as a point source, essentially treating it as a star, and then track how that point would appear to move across the Martian sky over 10 minutes, you can generate synthetic images, blur each position to account for the navcam's resolution, stack them, see what you get. Those simulations generally supported the artifact explanation. A moving point source, when tracked and stacked, produces an elongated streak. The length of the streak matches the distance traveled during the exposure time. It's basic kinematics plus image processing. But the simulations made assumptions. They assumed 3I Atlas was point-like, that its brightness was concentrated in a small nucleus. What if the coma was extensive? What if it was already dozens or hundreds of kilometers across at that distance? Then each frame wouldn't capture a point, but a fuzzy disk. Stacking fuzzy disks over time creates a different result than stacking points. The streak becomes smeared, less defined. The brightness distribution changes. And here's where it gets interesting. The images showed relatively sharp edges on the elongated feature. Not perfectly sharp, but sharper than you might expect if you were stacking images of a large, diffuse coma moving across the frame. That sharpness suggested either the coma was smaller than expected, the nucleus was brighter relative to the coma, or something about the structure was indeed elongated. Then there was the color analysis. Drew's point about the white center versus green edges wasn't easy to dismiss. Other amateur astronomers started pulling up their own ground-based observations from early September when 3I Atlas had been photographed during a total lunar eclipse. Those images, taken with tracking telescopes that compensated for the object's motion, showed 3I Atlas with what appeared to be an extended white core and a greenish halo. One astrophotographer, Gerald Raymond, who had imaged comets for decades, noted that the structure seemed atypical. Most comets show a bright nucleus with a gradually fading coma, more circular or slightly elongated in the direction of the sun due to radiation pressures pushing dust away. 3I Atlas in his images looked different. The white region appeared elongated even when properly tracked, and the green coma seemed to form a distinct layer around it rather than a uniform glow. If you took those ground-based observations seriously, they suggested the white, elongated appearance wasn't purely a Perseverance imaging artifact. It was already visible from Earth, though harder to see due to the much greater distance and atmospheric blurring. Professional astronomers began chiming in with caution. Several pointed out that determining the true shape of a comet from Earth or even from Mars orbit is fraught with challenges. You're not seeing the solid nucleus directly. You're seeing sunlight scattered by dust and gas surrounding the nucleus. The distribution of that dust and gas depends on how the nucleus is outgassing, which depends on its rotation, its surface composition, the angle of sunlight, and a dozen other factors. A spherical nucleus with uneven outgassing from active regions can create asymmetric comas that appear. But others noted that 3I Atlas had already proven itself unusual in multiple ways beyond just the shape debate. And this is where the conversation begins to widen beyond just two options about a photograph. The chemical composition kept coming up. Space-based observations from the James Webb Space Telescope in early August had shown something unexpected. Most comets are rich in water ice. When they approach the sun, water sublimates off the surface, creating the characteristic tails. But 3I Atlas was different. A spectrograph revealed that the coma was dominated by carbon dioxide, not water. 87% carbon dioxide by mass, 9% carbon monoxide, and only about 4% water. That ratio, 8:1 carbon dioxide to water, was extreme. Solar system comets typically show the opposite ratio, much more water than carbon dioxide. Some comets from the outer reaches of the solar system from the Oort cloud show higher carbon dioxide, but nothing like this. The only other interstellar comet, 2 Ice-Borisov, had shown water-dominated chemistry similar to solar system comets. Why was 3I Atlas so dry? One explanation involved temperature. If it formed in a colder region of its home star system, farther from its star than Earth is from our Sun, then water ice might have been depleted early in its history while carbon dioxide remained. Or if it had been wandering through interstellar space for billions of years, cosmic rays could have altered its surface composition. But there was another chemical oddity that compounded the mystery. Observations from the Very Large Telescope in Chile had detected nickel atoms in the coma. Nickel itself isn't shocking in comets. Many comets show trace metals, but 3I Atlas was producing nickel at an extraordinary rate, and critically, it was producing nickel without corresponding iron. In nature, nickel and iron are inseparable siblings. They form together in the cores of dying stars, get blasted into space together during supernova, and condense into planets and asteroids together. Every rock we've ever analyzed from space, every meteorite, every asteroid sample shows nickel and iron in roughly consistent ratios. They're chemically similar. They bond to similar materials. They don't separate naturally under normal conditions except in industrial processes. On Earth, we refine nickel away from iron when we want pure nickel for specialized alloys, for corrosion-resistant coatings, for high-temperature applications. Nickel plating, nickel-based superalloys used in jet engines and spacecraft components. These technologies require separating nickel from iron through chemical or electrochemical processes. The Very Large Telescope data showed nickel emission increasing dramatically as 3I Atlas approached the Sun. In just 1 month from July to August, the production rate had increased 25-fold. That steep rise following a power law relationship with the Sun's distance suggested something about the surface was being heated and releasing nickel preferentially. Natural explanations existed. Perhaps nickel carbonyl compounds, exotic molecules rarely seen in space, were sublimating off the surface while iron compounds remained stable. It would be unprecedented, but not physically impossible. Or perhaps the surface composition was layered with nickel-rich minerals on top and iron-rich materials beneath, and only the surface was hot enough to release metals. Yet the alternative explanation, the one that made headlines and raised eyebrows, was that the nickel signature matched what you'd expect from technological materials. If 3I Atlas was artificial, if it had a metallic hull or structural components, nickel alloys would make sense. They're durable, resistant to radiation, stable across wide temperature ranges, exactly what you'd want for a probe designed to travel between stars. But suggesting an object might be artificial based on chemical composition is a leap, a big one. It requires extraordinary evidence. And so far, all the observations could still be explained, however awkwardly, through natural processes. Strange natural processes, granted, processes we haven't seen before. But that's what makes interstellar objects interesting. They're samples from other planetary systems, places we can't visit, where conditions might have been very different from our solar system's formation. The debate over whether the elongation was real or artifact refused to resolve because both sides had points that couldn't be easily dismissed. And underneath it all was a growing realization. The photos were only part of the story. The chemistry was only part of the story. What mattered just as much was what we weren't seeing. The data that should have been released, but wasn't. The observations that multiple space agencies had made but refused to share. The silence that seemed to grow louder with each passing day. Chapter 3. The silence that screams. The peculiar thing about silence is that it only becomes noticeable when you are expecting noise. In the age of social media, instant updates, and space agencies competing for public attention, silence from multiple organizations simultaneously is deafening. Consider China's track record. The China National Space Administration has published over 14,000 images from the Tianwen-1 Mars orbiter since it entered orbit in 2021. These aren't just raw data dumps. They're carefully processed, beautifully rendered images released with accompanying press statements, often timed to coincide with national celebrations or to underscore China's growing capabilities in space. When Tianwen-1 captured a global color map of Mars at 76 meters per pixel resolution, the images were released within days. When the accompanying rover Zhurong landed on the Martian surface and began transmitting photos, China made sure the world saw them immediately. This isn't unusual. Space agencies use their successes to justify budgets, to inspire the next generation of scientists and engineers, to demonstrate technological prowess. During the Cold War, the space race between the United States and Soviet Union was as much about propaganda as it was about science. Every satellite launch, every human spaceflight, every lunar landing was a statement. We can do this. We are advanced. We are powerful. That competition never truly ended. It evolved. Today, China and the United States view each other as rivals in space. The Artemis Accords, an American-led framework for lunar exploration, deliberately excludes China. In response, China has partnered with Russia to plan an international lunar research station. The two powers barely coordinate. The Wolf Amendment, passed by the U.S. Congress in 2011, explicitly prohibits NASA from bilateral cooperation with China without special approval. They don't share data. They don't collaborate. They compete. So when 3I Atlas made its closest approach to Mars, and both NASA's Mars Reconnaissance Orbiter and China's Tianwen-1 had perfect vantage points to observe it, you would expect each agency to rush their results to publication. Imagine the headlines. China captures unprecedented images of interstellar visitor. NASA's MRO provides clearest view yet of mysterious comet. It's the kind of scientific achievement that plays well domestically and internationally, the kind that justifies funding and generates excitement. But neither released anything. Not processed images, not preliminary analysis, not even a brief statement confirming successful observations. NASA pointed to the government shutdown, which was real and did furlough thousands of employees. But the shutdown didn't prevent the Perseverance rover from continuing to post raw NavCam images automatically. Those images are uploaded through systems that run without human intervention, part of the mission's data management protocols. If raw NavCam images could still be posted, why couldn't raw HiRISE images? Why couldn't China, operating completely independently of American budget politics, release anything from Tianwen-1? The United Arab Emirates added another layer to the mystery. Their HOPE orbiter, the Emirates Mars mission, was designed specifically to study the Martian atmosphere across daily and seasonal cycles. It carries 3 instruments, including the Emirates Mars infrared spectrometer and the Emirates Mars ultraviolet spectrometer. Perfect tools for analyzing the coma of a comet, for detecting chemical signatures, for measuring how gases interact with solar radiation. And HOPE had a clear line of sight to 3I Atlas during the October 3rd flyby. The UAE has been extraordinarily proud of HOPE. It was the Arab world's first interplanetary mission, arriving at Mars in February 2021. The mission team regularly publishes data, releases updates, and engages with the public. The UAE Space Agency maintains an active social media presence. They celebrate their achievements. They share their science. Yet after October 3rd, nothing. No images of 3I Atlas, no spectroscopic data, no mention of observations beyond a brief pre-flyby statement confirming they would be observing. It was as if the events simply didn't happen from their perspective. Despite months of anticipation, ESA, the European Space Agency, represented yet another puzzle. Their Mars Express and ExoMars Trace Gas Orbiter were both positioned to observe. ESA had announced in September that observations would take place between October the 1st and 7th. They specified that Mars Express would use its high-resolution stereo camera and spectrometers, while the Trace Gas Orbiter would employ its color and stereo surface imaging system and its own suite of instruments. These weren't casual observations. They were planned, scheduled, coordinated efforts involving multiple teams across European nations. And then silence. The ESA website showed no updates about 3I Atlas observations beyond the original announcement. No press releases, no preliminary findings, no images. For an agency that routinely shares spectacular images of Mars, that publishes results from its many missions with regularity, the absence felt deliberate. When observers began pointing out this coordinated silence across geopolitical lines, some interesting historical parallels were raised. There have been moments when rival nations cooperated on matters of mutual interest. The Partial Nuclear Test Ban Treaty of 1963, signed by the United States, Soviet Union, and United Kingdom at the height of the Cold War, recognized that atmospheric nuclear testing threatened everyone regardless of political ideology. Space rescue agreements followed. The Apollo-Soyuz test project in 1975 saw American and Soviet spacecraft dock in orbit, crews shaking hands in space while their nations remained in ideological opposition on Earth. The common thread: shared existential stakes. When something threatens everyone equally, or when something affects the entire species, rivalry becomes secondary to survival or understanding. The 1998 United Nations Office for Outer Space Affairs has guidelines, though not binding treaties, about how nations should handle the detection of extraterrestrial intelligence. These protocols emphasize that no single nation should make unilateral announcements. Confirmation should be verified. The international community should be informed. Premature disclosure could cause panic, misinformation, or international incidents. If, and this is a significant if, the Mars orbiters observed something that genuinely challenged the assumption that 3I Atlas is a natural object, you could construct a scenario where coordinated silence makes sense, not as conspiracy, but as protocol, as caution, as an attempt to verify findings before making statements that cannot be retracted. But that requires believing something extraordinary was observed. And extraordinary claims, as the saying goes, require extraordinary evidence. The silence alone isn't evidence of anything, except that images haven't been released. There could be mundane explanations. Data processing takes time. Quality control requires careful review. Scientists want to publish findings in journals, not through press releases, to maintain credibility and priority of discovery. Government shutdowns, even partial ones, disrupt workflows and delay publications. Yet the pattern remained troubling. 5 space agencies representing the United States, Europe, China, and the United Arab Emirates, all with functioning Mars missions, all positioned to observe the same event, all choosing not to share results in the immediate aftermath. 5 agencies that don't typically coordinate, that compete for prestige and funding, suddenly aligned in their silence. Online communities began tracking this obsessively. Reddit threads on R space and R astronomy accumulated hundreds of comments analyzing every angle. People noted that Tianwen-1 routinely posted images within 48 to 72 hours of acquisition. They pointed out that ESA had shared Mars Express images just days after capture. In previous instances, they highlighted that the UAE's HOPE mission had a public data portal designed for transparency. Someone noted that on October 1st, just 2 days before the flyby, China's Tianwen-2 mission, an entirely separate spacecraft en route to collect samples from an asteroid, released a selfie image showing Earth in the background. It was a propaganda piece, beautifully composed, showing China's flag on the spacecraft with our planet as backdrop. The timing struck observers as significant. China was perfectly capable of releasing space images during the exact time frame when 3I Atlas observations should have been processed. They chose to release a Tianwen-2 image. They chose not to release Tianwen-1 observations of the interstellar visitor. Was it meaningful, or was it reading patterns into noise, seeing conspiracy where there was only coincidence? The silence spawned theories. Some argued all the agencies saw nothing remarkable, that 3I Atlas appeared exactly as expected, a comet, and thus there was no urgency to rush results to press when papers could be written properly. But that didn't explain why China wouldn't leverage even mundane observations for prestige. Others suggested technical failures, that perhaps all the instruments malfunctioned simultaneously, but the odds of that seemed vanishingly small. The more provocative theories suggested deliberate suppression, that high-resolution images revealed structure, geometry, something that couldn't be easily explained as natural. That spectrographic data showed chemical signatures inconsistent with any known comet. That multiple agencies recognized they were looking at something that required coordination to announce properly, if it was announced at all. One blogger compiled a timeline showing that in the 72 hours after the October 3rd flyby, various government officials and scientists had appeared on news programs discussing 3I Atlas. JWST had been interviewed on Newsmax, sharing the screen with Representative Tim Burchett, a member of the House Committee on Oversight and Accountability. During a separate news segment, Stephen Miller, Deputy Chief of Staff for Policy at the White House, was asked directly whether the president had been briefed on 3I Atlas. Miller's answer was diplomatic and vague, reassuring the public that appropriate agencies were monitoring the situation, but offering no specifics about briefings or findings. That White House officials were even being asked about an astronomical object, that it had risen to the level of presidential briefings, suggested this was being taken seriously at levels beyond just scientific curiosity. The fact that a congressional representative was appearing on television to discuss it, that questions about 3I Atlas were being directed to White House staff, that the media was covering it as a developing story rather than just a science curiosity, all of it pointed to an event that had transcended typical astronomical observations. And yet, the core data remained locked away. The HiRISE images, capable of resolving features 30 kilometers across at 3I Atlas's distance during closest approach, would show whether the brightness came from a massive nucleus or something else. They would reveal actual structure, if structure existed. They would put to rest or intensify the debates about elongation, about shape, about what this object fundamentally is. Those images existed. They had been captured. Somewhere in NASA's databases on servers that survived the shutdown, the highest resolution photographs of an interstellar object ever taken by human instruments were sitting, processed, or awaiting processing, and no one was showing them to the world. The silence continued. Days passed. October 6th, October 7th. Speculation intensified in the vacuum, and while the world waited for official images that never came, another peculiarity of 3I Atlas began attracting attention. Something visible in the amateur observations that had been captured before it disappeared behind the sun from Earth's perspective. something that added yet another layer of mystery to an already bewildering object. It had changed color from red to green, and no one could quite explain why. Chapter 4. Green, glowing, and mysterious. Color in astronomy is information. When an object in space appears red, blue, green, or any other hue, it's telling you about its composition, its temperature, the processes occurring on or around it. Sunlight is white, containing all visible wavelengths. When that white light hits a comet, some wavelengths get absorbed by molecules in the coma, and others get re-emitted through fluorescence. The color you see is the chemical signature of what's there. Green comets are not particularly rare. Many comets develop a greenish glow as they approach the sun, and the cause is well understood. A molecule called diatomic carbon, written as C2, forms when larger carbon-containing molecules in the coma get broken apart by ultraviolet sunlight. This C2 molecule absorbs UV light and re-emits it at specific wavelengths in the green part of the spectrum, around 510 nanometers. It's a beautiful process, and it's so common that astronomers expect to see it in active comets that contain carbon-rich materials. 3I Atlas was observed extensively in July and early August. During that period, it appeared reddish. The reddish color indicated dust particles reflecting sunlight with a slight bias toward longer wavelengths. This made sense for a comet far from the sun, where sublimation was still minimal, and the coma consisted mostly of dust grains being gently released from the warming nucleus. Red meant dust, normal, expected. Then came September the 7th, 2025. A total lunar eclipse was visible from certain locations on Earth, including Namibia. During a total lunar eclipse, the moon moves into Earth's shadow, and the sky becomes darker than usual for a full moon night. This creates ideal conditions for observing faint objects without the glare of moonlight washing them out. It's a gift to astronomers. A few hours of darker skies without having to wait for a new moon. Two experienced astrophotographers, Michael Yeager and Gerald Riemann, were in Namibia with their equipment pointed at 3I Atlas. Both had imaged comets for decades. They knew what to expect, how comets typically behaved, what colors they usually displayed at various distances from the sun. Their telescopes tracked 3I Atlas across the sky, compensating for Earth's rotation and the comet's motion to keep it centered in long exposures. When they processed their images, something had changed. 3I Atlas was no longer reddish. It glowed green, a distinct emerald-tinged hue that extended into a coma roughly 2.5 arc minutes across. The shift was dramatic and unambiguous from one color to another in the span of weeks. Yeager posted the images online with the caption noting the green to blue-green gas coma. He mentioned that a faint tail was also visible in the images from September 9th. The astronomy community took notice immediately. A color change from red to green meant the comet's activity had increased, that gases were now dominating the coma rather than just dust. It suggested 3I Atlas was entering a more active phase as solar heating intensified. But here's where it gets strange. When scientists looked at the spectroscopic data, the detailed analysis of which wavelengths were being emitted, they couldn't find significant amounts of diatomic carbon. Several teams had obtained spectra of 3I Atlas in late August and early September using professional telescopes. A paper published by Luis Salazar Manzano and colleagues at the University of Michigan specifically addressed this. They found an extremely low ratio of C2 to cyanogen. So low, in fact, that they concluded 3I Atlas was among the most carbon chain depleted comets ever observed. Let that sink in. The comet appeared green, strongly suggesting diatomic carbon fluorescence. But spectroscopic analysis showed the molecule responsible for that green glow was essentially absent. It's like seeing smoke without fire, hearing a bell that isn't ringing. The effect was present, but the cause was missing. Several explanations were proposed. One involved the timing and location of observations. Perhaps C2 was present, but in small amounts, and the green glow was being generated efficiently enough to be visible even with depleted C2. Fluorescent efficiency can vary. A small amount of a highly efficient fluorescent can produce a noticeable glow. Another possibility involved different molecules producing green or blue-green light. While C2 is the most common culprit, other molecules can fluoresce in similar wavelengths. The trick is figuring out which ones, because you need molecules that are plausible in a comet's environment and that respond to solar UV radiation in the right way. This is where cyanide enters the story. Not the poison you see in detective novels, though it's chemically related. Cyanogen, or CN, is a radical formed from carbon and nitrogen. It's common in comets. When CN absorbs UV light, it can emit in the violet and blue parts of the spectrum. AI Loeb, analyzing the same data that showed extreme nickel production, noted that cyanogen production from 3 Atlas was increasing steeply as it approached the Sun. The rate followed a power law rising with heliocentric distance to the power of 9.38. That's an incredibly steep dependence, much steeper than typical comets. Could cyanogen be responsible for the green appearance? Possibly. CN emission bands do extend into blue-green wavelengths under certain conditions. If CN was present in unusually high concentrations, and if dust scattering and other factors were contributing to the color perception, the combination might produce the observed green hue without requiring large amounts of C2. But this explanation requires 3-eyed Atlas to have a very unusual chemistry, not just depleted in carbon chains, but simultaneously enriched in nitrogen-bearing molecules like CN. Why would an interstellar comet have this particular combination? What processes during its formation, or during billions of years wandering through the galaxy, would create such a lopsided composition? Natural comets from our solar system show a range of compositions based on where they formed. Comets from the Oort cloud, the distant spherical shell of icy bodies surrounding the solar system, tend to have different ratios of volatiles than comets from the Kuiper belt, the flattened disk of objects beyond Neptune. The differences relate to temperature during formation, to how much processing they've undergone from solar radiation, to whether they've made previous passes near the Sun. But 3 Atlas didn't form in our solar system. It formed somewhere else around another star, under conditions we can only infer. Maybe its home system had different elemental abundances. Stars form from clouds of gas that aren't perfectly mixed. Some regions of the galaxy are richer in certain elements than others based on the history of supernovae that enrich those regions. A star forming in a nitrogen-rich environment might produce comets with unusual nitrogen to carbon ratios. Or maybe 3-eyed Atlas is old. Estimates based on its velocity and trajectory suggest it could be 7 to 14 billion years old, possibly twice the age of our Sun. If it's that ancient, it would have formed during a period astronomers call cosmic noon, when star formation in the Milky Way was at its peak. Conditions then were different. More supernovae, more radiation, denser stellar environments. Perhaps comets from that era naturally have different compositions than those forming today. These are reasonable speculations. They're grounded in astrophysics, in our understanding of stellar evolution and galactic history. They allow 3-eyed Atlas to remain a natural object while still being profoundly strange. But there's a competing thought that refuses to go away. If you were designing a probe to travel between stars, what would you use as propellant? chemical rockets are inefficient for interstellar distances. You'd need something more exotic. Ion drives that expel particles at extremely high velocities, perhaps. Or if you were being clever, you might harness solar energy when passing close to stars, sublimating volatile materials to produce thrust, using the star's own radiation to power your trajectory adjustments. If you wanted a probe to look like a comet to any observers, you might coat it with ices with volatiles that would sublimate predictably as it approached a star. Carbon dioxide ice would be a reasonable choice. It's stable at very low temperatures, common in space, and sublimes vigorously when heated. If you needed to produce thrust for small maneuvers, controlled sublimation of CO2 from specific vents could do it. And if your probe used nitrogen-based propellants or coolants, leaks or deliberate releases might produce cyanogen as those materials interacted with solar radiation. This is speculation. It's important to emphasize that there's no direct evidence that three-eyed Atlas is artificial. But the chemical peculiarities, the carbon chain depletion alongside steep cyanogen production, the appearance of green coloration without the expected molecules, all of it creates a pattern that's difficult to fit into standard cometary models. One astronomer speaking anonymously to a science journalist noted that if you made a list of all the observations of three-eyed Atlas and asked how many could be easily explained by natural comet processes, you'd get a mixed answer. Some things fit. Active comets outgas. They produce comas. They sometimes show unexpected chemistry. But when you look at the entire suite of observations together, the combined probability of all these anomalies appearing in a single natural object starts to feel uncomfortable. It's a Bayesian problem. Each individual oddity might be unlikely, but possible. Green color without much C2. Rare, but maybe it's CN or something else. Nickel without iron. Bizarre, but perhaps some exotic chemical process. Carbon dioxide dominance, unusual for comets we're familiar with, but not impossible for an object from another system. Elongated shape could be an imaging artifact, or could be a legitimate uncommon geometry. But multiply the probabilities together. If each anomaly has a 10% chance of occurring naturally, and you observe 7 independent anomalies, the combined probability is 0.1 to the 7th power. That's 1 in 10 million. Now, the anomalies might not be fully independent. Some could be related, sharing common causes, and the individual probabilities are largely guesses. We don't have enough examples of interstellar objects to calculate real statistics. But the exercise illustrates why some scientists were starting to feel that invoking natural explanations for everything about three-eyed Atlas required stretching plausibility, not breaking it, but stretching it thin. The green glow faded in subsequent weeks as three-eyed Atlas moved closer to the sun and eventually disappeared from Earth's view behind solar glare. By late September, ground-based observations were no longer possible. The object was too close to the sun's position in the sky, lost in the overwhelming brightness. It would remain unobservable from Earth until early December, when it would emerge on the other side of the sun, having completed its perihelion passage. That meant the Mars flyby on October 3rd was one of the last opportunities to study three-eyed Atlas before it reached its most active state near perihelion. And when those observations remained unreleased, when the silence from space agencies continued, the green mystery became one more piece of a puzzle that refused to resolve into a coherent picture. What was 3 Atlas? A chemically bizarre natural comet with an unlikely but possible set of properties, or something that merely resembled a comet while being fundamentally different? The answer, many believed, lay in the metal signature that kept intensifying, the nickel production that defied easy explanation. And perhaps most troubling, the pattern of how that nickel was being released, like something activating, rather than something passively sublimating. Chapter 5. Industrial Alloys from Deep Space. The Very Large Telescope in Chile is not a single instrument, but an array of 4 massive telescopes, each with a primary mirror 8.2 meters across. When combined through interferometry, they can achieve resolution equivalent to a telescope over 100 meters in diameter. It's one of the most powerful ground-based observatories in the world, operated by the European Southern Observatory, and it's been observing Three-Eyed Atlas since July. The UVES spectrograph, the ultraviolet and visual Echelle spectrograph, is particularly good at detecting faint emission lines from metals. When atoms of elements like iron, nickel, sodium, or calcium are present in a comet's coma and get excited by solar ultraviolet radiation, they emit light at very specific wavelengths. These emission lines are like fingerprints. Each element produces a unique pattern, and the intensity of those lines tells you how much of that element is being released. The team monitoring 3 Atlas with UVEs included Rohan Rahat Gaon and colleagues. They were specifically looking for metal emissions because previous observations of comets had shown that detecting metals was possible but challenging. The temperatures in most comets are far too low to vaporize the minerals containing these elements. You typically need temperatures above 1,000 Kelvin to sublimate silicate or metallic grains. Most comets, even active ones, don't reach those temperatures until they are extraordinarily close to the Sun. Yet Three-Eyed Atlas was producing metal emissions when it was still beyond 3 astronomical units from the Sun. That's 3 times farther from the Sun than Earth is. At that distance, solar heating is weak. The sunlight intensity drops with the square of distance. 3 times farther means 9 times less solar energy per square meter. It should be far too cold for metals to sublimate. But there they were, nickel emission lines, clear and unmistakable. And as Three-Eyed Atlas moved closer to the Sun, those lines didn't just brighten gradually, they exploded. Between late July and late August, covering a distance change from roughly 3.9 AU to 3.1 AU, the nickel production rate increased by a factor of 25. 25 times more nickel per second in just 1 month. The team modeled this increase and found it followed a power law. The production rate scaled with heliocentric distance raised to the power of 8.43 plus or minus 0.79. That's an extraordinarily steep relationship. For comparison, most cometary emissions scale with distance raised to somewhere between -2 and -4. Water sublimation typically follows an inverse square relationship, -2, because it's driven by solar heating, which itself follows an inverse square law. A power of 8.4 means the production rate is exquisitely sensitive to distance. Get even slightly closer to the Sun, and the emission rate jumps dramatically. It's not a gentle increase, it's explosive. And that pattern doesn't match simple thermal sublimation of surface ices. Then there's the iron problem, or rather the lack of iron problem. The same observations that detected nickel emission also searched for iron emission lines. Iron should be there. In every meteorite, in every asteroid, in every sample of cosmic material ever analyzed, nickel and iron appear together. The ratio varies slightly depending on the specific mineral, but they're always both present. In the early observations of Three-Eyed Atlas, iron wasn't detected at all. As the comet moved closer and the nickel signal grew stronger, iron finally appeared, but only when Three-Eyed Atlas was inside 2.64 AU. And even then, the nickel-to-iron ratio was extreme, much higher than any solar system comet or the previous interstellar comet, ʻOumuamua or Borisov. The authors of the study described this as extremely puzzling. That's scientific understatement. When researchers use phrases like extremely puzzling or unprecedented in a peer-reviewed paper, they're signaling that they've exhausted conventional explanations and are entering territory where new physics or chemistry might be required. Why is nickel separating from iron? In terrestrial industry, we know exactly how to do this. The MOND process, developed in the 1890s, uses carbon monoxide to form nickel carbonyl, a volatile compound that can be separated from iron riches. You heat the ore with carbon monoxide at moderate temperatures. Nickel reacts to form nickel carbonyl gas, which boils at 43 degrees Celsius. You collect the gas, then heat it to higher temperatures, where it decomposes back into pure nickel metal and carbon monoxide. The CO is recycled. You're left with refined nickel. It's how we make high-purity nickel for electronics, for corrosion-resistant alloys, for the nickel plating that protects steel components. It's industrial chemistry perfected over more than a century, standard in metallurgy textbooks. And it's apparently happening on Three-Eyed Atlas. Maybe the natural alternative requires invoking nickel carbonyl formation through processes we've never observed in comets. If the comet contains nickel-bearing minerals and carbon monoxide, which we know it has in abundance, then solar heating could potentially drive reactions that form nickel carbonyl. That compound is volatile enough to sublimate at relatively low temperatures, much lower than the temperatures needed to vaporize metallic nickel or nickel silicates. Iron could remain bound in different minerals that don't form analogous volatile compounds under the same conditions. Iron carbonyl exists, but it requires different formation conditions. If the mineralogy of Three-Eyed Atlas is just right, with nickel preferentially available in forms that can react with CO, while iron is locked in more stable compounds, you could theoretically get the observed separation. But that's a lot of ifs. It requires a very specific mineralogical composition, unlike anything seen in solar system comets. It requires conditions that preferentially form nickel carbonyl while suppressing iron carbonyl. And it requires that these exotic conditions be common enough that an interstellar comet would naturally exhibit them, despite interstellar comets being incredibly rare, and this being only the third we've detected. The alternative is that the nickel signature isn't coming from natural sublimation at all, that it's coming from a manufactured surface. Nickel is extensively used in spacecraft construction. Nickel alloys are favored for components exposed to radiation, extreme temperatures, and corrosive environments. Fuel tanks are often nickel-plated. Structural elements and satellites use nickel steel or nickel titanium alloys. Even spacecraft that land on planets, like the Mars rovers, use nickel in their wheel mechanisms, in their joints, in their electronic shielding. If Three-Eyed Atlas were artificial, if it had a metallic hull or structural framework, then solar heating as it approached the sun would cause surface materials to outgas. Coatings would vaporize. Any volatile compounds on the surface, including those used for thermal control or as protective layers, would sublimate. If the structure used nickel-rich alloys, which would make sense for an interstellar probe needing durability and radiation resistance, then you'd expect to see nickel emission. And you'd expect it to follow a steep power law if the emission was being driven by a threshold effect. Imagine a probe covered with a layer of insulating material, perhaps accumulated during billions of years in interstellar space. As solar heating intensifies, the outer layers sublimate first, but underneath the metallic structure remains protected. Then, at a certain temperature threshold, the insulation layer becomes thin enough that heat reaches the metal surface. Once that happens, the metal itself begins to heat rapidly, and any volatile compounds associated with it start vaporizing. That transition would be sharp. Below the threshold, minimal emission. Above it, rapidly increasing emission, as more of the metallic surface becomes exposed and heats up. The steep power law relationship would naturally emerge from this kind of threshold-activated process. Is this what's happening? There's no way to know without more data, but the pattern is consistent with activation rather than passive thermal sublimation. It looks like something turning on rather than something gradually warming up. Other metals were searched for in the spectra. Sodium, which is common in many solar system comets and produces bright yellow emission lines, wasn't detected in significant amounts. Calcium, another metal sometimes seen in comets, was absent. It was specifically nickel, with its distinctive green emission lines that dominated the metal signature. The temperature puzzle deepened when researchers calculated what surface temperatures would be needed to explain the observations. Even at 2.1 AU, three-eyed Atlas should have a surface temperature of only around 200 Kelvin, far below the roughly 1,000 Kelvin needed to sublimate silicate minerals, yet nickel was being released efficiently. Either the comet's surface was much hotter than simple thermal models predicted, perhaps due to some exotic greenhouse effect or subsurface heat source, or the nickel wasn't coming from direct sublimation of minerals, but from some other process. Nickel carbonyl formation would work at lower temperatures, which is why it's the favored natural explanation. But forming it requires the right chemical environment, the right minerals, the right ratios of reactants. And there's one more detail that caught attention. The cyanogen production followed an even steeper power law than the nickel. The CN emission rate scaled with distance to the power of 9.38. If you're invoking natural chemistry to explain both the nickel and the cyanogen, you need whatever process is happening to produce both in rapidly increasing amounts with slightly different but consistently steep dependencies on solar distance. Cyanogen is of course toxic to Earth life in most of its forms. Hydrogen cyanide, HCN, is used in chemical weapons and executions, but CN, the cyanogen radical, is different. It's common in comets formed from ammonia or other nitrogen-bearing molecules when they are broken apart by UV light. Finding CN in a comet isn't surprising. Finding it at the observed production rates with such a steep distance dependence is. Put the nickel and cyanogen together, both increasing steeply, both following power laws that suggest threshold effects or activation rather than simple thermal sublimation, both defying easy explanation through conventional cometary chemistry. And both, interestingly, are molecules that have industrial or technological relevance: nickel in alloys and plating, cyanide compounds in chemical synthesis and materials processing. Is it a coincidence? Are we seeing natural processes that happen to mimic what we'd expect from technology? Or are we looking at signatures that are technological, that were designed, that serve purposes beyond random outgassing? The observations couldn't answer that question definitively, but they added weight to the growing sense that 3 Atlas was unlike any comet humanity had studied before. And with perihelion approaching on October 29th, when the comet would reach its closest point to the Sun at just 1.36 AU, the metal emissions would reach their peak intensity. If the patterns held, if the power laws continued to their logical conclusion, the nickel production would increase by additional orders of magnitude in the final weeks. That moment when solar heating was at maximum, when outgassing would be most intense, when any surface materials would be vaporizing under extreme thermal stress, that would be the moment of truth. Would 3I Atlas behave like a comet pushed to its limits, possibly fragmenting or producing a spectacular outburst? Or would it behave like something engineered, perhaps using the solar energy for propulsion, for trajectory adjustments, for purposes we could only speculate about? The metal signature was a clue. But like all clues in this strange case, it pointed in multiple directions simultaneously, refusing to resolve into certainty. And while scientists debated nickel-carbonyl versus spacecraft alloys, another set of anomalies demanded attention. The trajectory itself, the path 3I Atlas was following through the solar system, displayed its own peculiarities, mathematical improbabilities that strained the boundaries of coincidence. Chapter 6. 7. Impossible Things Before Perihelion. Avi Loeb has become a polarizing figure in astronomy. To his supporters, he's a rare scientist willing to challenge orthodox thinking, to ask uncomfortable questions, to consider possibilities that others dismiss reflexively. To his critics, he's too quick to invoke extraordinary explanations when mundane ones might suffice, too eager for media attention, too willing to publish provocative ideas before they've been thoroughly vetted by the community. But his credentials are undeniable. Former chair of Harvard's astronomy department, founding director of the Black Hole Initiative, over 800 published papers, awards, and honors from institutions around the world. When he speaks about astrophysics, people listen, even if they disagree. And in early October, on the day 3 Atlas made its closest approach to Mars, Loeb published a summary of what he called the 7 anomalies of this interstellar visitor. Some of these have been mentioned already, but understanding them as a complete set, seeing how they interrelate and compound each other, that's where the real weight of the mystery becomes apparent. The first anomaly concerned size and mass. When 3 Atlas was discovered in July, astronomers measured its brightness and tried to work backward to determine how big it must be. If you assume the object reflects about 5% of the sunlight hitting it, a typical albedo for asteroids and cometary nuclei, then the brightness observed from Earth implies a diameter of roughly 20 kilometers. 20 kilometers is enormous for an interstellar object. ʻOumuamua was estimated about 100 m across, roughly the length of a football field. 2I Boris, the second interstellar visitor, was somewhere around 1 kilometer in diameter. Now, here was 3I Atlas potentially 20 times larger than Boris and 200 times larger than ʻOumuamua. The problem with large interstellar objects is that they should be exceedingly rare. Planetary systems don't eject their biggest members easily. When planets form and gravitational interactions scatter objects outward, it's the smaller bodies that get kicked out. The larger an object, the more gravitational binding energy it has to its home system, the harder it is to achieve escape velocity. You'd expect interstellar space to be populated mostly by small debris, with large objects becoming exponentially rarer as size increases. Loeb calculated that if 3I Atlas really is 20 kilometers across, then detecting it within 5 years of continuous sky surveys implies a mass supply of interstellar objects that's untenable. The Milky Way would need to be producing and ejecting objects at this scale at rates far higher than stellar and planetary system formation models allow. It would require almost every star system to eject massive planet decimals, a scenario that contradicts everything we understand about planetary dynamics. The alternative: the object isn't 20 kilometers of solid rock. Most of the brightness comes from a large extended coma of dust and gas with a much smaller nucleus hidden inside. That would make sense for a comet and bring the mass down to reasonable levels. But then you have to explain why this comet shows all the other anomalies, why its chemistry is so bizarre, why it's producing metals at impossible rates. The second anomaly is the forward jet. When Hubble Space Telescope imaged 3I Atlas on July 21st, the pictures showed something unusual. Scattered sunlight appeared to extend toward the sun, not away from it. Comets develop tails that point away from the sun because radiation pressure and solar wind push gas and dust outward. The tail always points generally anti-solar, like a windsock showing which way the solar wind is blowing. But 3 Atlas showed the opposite. a sunward extension of brightness, what astronomers call an anti-tail. Low and his colleague Eric Kito analyzed the Hubble image carefully and determined that the glow extended about 10 times farther toward the Sun than it did perpendicular or away from the Sun. Factor in the viewing geometry, the angle from which Hubble was observing, and the 10-to-1 ratio becomes even more extreme. Anti-tails aren't completely unknown. Some comets develop them due to specific geometric effects, where dust grains released earlier in the orbit remain in the comet's orbital plane and appear to point forward when viewed from certain angles. But those are usually temporary, appearing and disappearing as viewing geometry changes, and they don't typically show the extreme elongation ratio that 3 Atlas displayed. A forward jet could indicate active venting from the sunward side of the nucleus. If volatiles are sublimating preferentially from the hemisphere facing the Sun and being expelled with enough velocity to overcome radiation pressure momentarily, you could get a sunward plume. But that requires very specific conditions, very active outgassing. And it still doesn't explain the extreme elongation or the persistence of the feature across multiple observations. The third, fourth, fifth, and sixth anomalies all relate to the trajectory, and this is where statistics become uncomfortable. 3 Atlas entered the solar system on a retrograde orbit, moving opposite to the direction planets orbit the Sun. Its orbital plane is tilted by about 5 degrees relative to the ecliptic, the plane in which Earth and most planets orbit. 5 degrees doesn't sound like much, but space is 3-dimensional. If interstellar objects arrive from random directions, which they should because there's no reason for them to preferentially approach from any particular angle, then the probability of an orbit being within 5 degrees of the ecliptic plane is roughly the solid angle of that zone divided by the total solid angle of a sphere. The calculation gives you about 0.2%, 1 in 500. Not impossible, but unlikely. If 3 Atlas arrived randomly, you'd expect it to come from any direction with equal probability. The ecliptic plane is special to us, to our solar system, because it's where the planets are, but it has no special significance in interstellar space. So why is this interstellar visitor aligned with it? Then consider the close approaches. 3 Atlas passed within 29 million kilometers of Mars on October 3rd. It will pass near Venus. Its trajectory will bring it relatively close to Jupiter in March 2026. These aren't impacts or even particularly close flybys by cosmic standards, but they're closer than you statistically expect for a random trajectory. Low calculated the probability that an interstellar object entering the solar system on a random trajectory would happen to pass near multiple planets. The answer depends on how you define near, but using reasonable definitions of close approach distances, the combined probability comes out to roughly 0.005%, 1 in 20,000. Again, not impossible. Unlikely things happen. Lottery winners exist despite odds of millions to 1. But you start to wonder when unlikely things keep accumulating. The timing matters too. Planets orbit at different speeds. Mars takes about 687 days to complete one orbit. Jupiter takes almost 12 years. Venus takes 225 days. The probability that an interstellar object arrives not only on a trajectory that passes near all 3 planets, but also arrives at times when each planet happens to be in the right location in its orbit for a close approach. That probability multiplies the already low trajectory probability by another factor. Low's rough estimate for the combined probability of both the trajectory alignment and the timing working out is about 1 in 200,000. You're stacking unlikely events on top of each other. The 7th anomaly is perhaps the most speculative, but also the most intriguing. The arrival direction of 3EI Atlas, when traced back into interstellar space, comes from a region of the sky near Sagittarius. Not surprising in itself. Sagittarius is toward the galactic center, a direction rich in stars. But Lowe noted that this direction is within 9 degrees of another famous signal from that general region. On August 15, 1977, the Big E radio telescope in Ohio detected a strong narrowband radio signal that lasted 72 seconds. The signal was exactly at the frequency where neutral hydrogen naturally emits, a frequency that many SETI researchers believe is a logical choice for interstellar communication because any technological civilization would know about it. The signal was so unusual, so apparently artificial in character, that astronomer Jerry Ayan wrote "wow" next to it on the computer printout. It became known as the "wow" signal. Despite many attempts, the signal has never been detected again. Explanations range from terrestrial interference to a passing comet that somehow produced a signal at the right frequency, to yes, an extraterrestrial transmission. The mystery remains unsolved nearly 50 years later. Is it meaningful that 3I Atlas's trajectory, when traced backward, points to within 9 degrees of the WOW signal's origin? Lowe calculated the probability of this alignment as roughly 0.6%, better odds than some of the other coincidences, but still unlikely. But here's the question. If you're an extraterrestrial civilization and you send a probe to a solar system you've detected, perhaps through radio transmissions from that system, or through transit observations of planets crossing in front of their star, how would you announce your arrival? You might send a radio signal first, a "hello, we see you" message. Then, if you wanted to send a physical probe, you might send it along the same trajectory from the same location, so that anyone connecting the dots would realize the signal and the probe were related. It's speculative. Connecting 3 Atlas to the WOW signal requires believing both are artificial and related, which is a leap beyond what the data supports. But the alignment exists. It's documentable, and it adds one more layer to a picture that's already strained with improbabilities. When you list them out, the 7 anomalies create a cumulative weight. Large size for an interstellar object, a jet contradicting normal cometry behavior, extreme chemical composition with nickel without iron and carbon dioxide dominance, green color without the molecules that should cause it, trajectory aligned with the ecliptic plane, arrival time optimized for planetary flybys, and arrival direction aligned with a historic anomalous radio signal. Each anomaly has possible natural explanations, stretched explanations in some cases, explanations requiring special circumstances or poorly understood chemistry, but explanations nonetheless. Science works by finding natural explanations for observations. It's only when natural explanations become more contrived and improbable than artificial ones that you're forced to seriously consider the latter. And that threshold is subjective. It depends on your prior beliefs about how likely artificial explanations are. If you think the probability of encountering alien technology in our solar system is essentially 0, then no amount of anomalies will convince you. You'll always prefer even highly improbable natural explanations because they're still more likely than aliens. But if you allow even a small prior probability that interstellar probes could exist and might occasionally pass through our solar system, then each anomaly updates that probability upward. Multiple anomalies compound. What started as a very small probability becomes less small. Still unlikely, perhaps, but not dismissible. Lowe has been explicit about this. He said repeatedly that 3 Atlas is most likely a natural comet. But he argues, and this is where the controversy lives, that the possibility of it being artificial should be investigated seriously. that we should collect as much data as possible, that we should use our best instruments, point radio telescopes at it, analyze every spectrum, track any deviations from purely gravitational motion. Because if there's even a 1% chance, even a 0.1% chance that we're witnessing a probe from another civilization, the implications are so profound that we have a responsibility to check thoroughly. The cost of being wrong is small. We observe an unusual comet and learn something about interstellar chemistry. The cost of ignoring it if it's artificial, we miss first contact. This reasoning divides the scientific community. Some see it as appropriate caution and open-minded investigation. Others see it as sensationalism, as lowering standards of evidence to chase after unlikely scenarios. The debate reflects deeper questions about how science should handle truly anomalous observations, how we balance skepticism with curiosity, how we decide when something is weird enough to warrant exceptional attention, and all of it, the 7 anomalies and the arguments about what they mean, would reach a critical moment on October 29th, when 3 IATALs passed perihelion and faced the full force of solar radiation at its closest approach to the Sun. Chapter 7. What the Politicians Know. There's a peculiar protocol in Washington. When scientific matters intersect with national security, information flows through channels that the public never sees. Intelligence briefings happen behind closed doors. Congressional committees with security clearances receive updates that don't make it into press releases, and sometimes carefully chosen words in public statements reveal that people in positions of authority know more than they're saying. The question started appearing on October 2nd, the day before 3 Atlas reached its closest approach to Mars. Stephen Miller, serving as Deputy Chief of Staff for Policy at the White House, was making the rounds on news programs discussing the government shutdown. Routine appearances explaining budget negotiations and operational continuity. But then, on one program, a journalist asked a question that seemed to catch Miller slightly off guard. Had the president been briefed on 3 Atlas? Miller's response was measured, calibrated. He confirmed that appropriate agencies were monitoring the situation. He offered reassurances about scientific competence and thoroughness. He emphasized that there was no danger to Earth, that the object would pass far from our planet. But he didn't actually answer whether the president had been briefed. He didn't confirm or deny. He pivoted to talking about the capabilities of American space programs and the importance of continued investment in NASA. The non-answer was itself informative. If 3 Atlas were just an interesting astronomical object, a natural comet passing through, the expected response would be simple. No, the president hasn't been briefed on individual astronomical observations. There are thousands of astronomers making discoveries daily. Presidential briefings cover matters of national importance, security threats, diplomatic crises. A comet, however unusual, wouldn't typically rise to that level. But Miller didn't say that. He didn't dismiss the question as absurd. Instead, he acknowledged it seriously, spoke about monitoring, used language that suggested ongoing attention from federal agencies. That choice of words, that reluctance to simply say no, it suggested 3 Atlas had indeed reached levels of government where decisions about information management are made. Around the same time, Representative Tim Burchett from Tennessee appeared on Newsmax. Burchett serves on the House Accountability, a committee that has jurisdiction over federal agencies, including NASA. He's been vocal about transparency, particularly regarding unidentified aerial phenomena, pushing for declassification of government files and public disclosure of what agencies know about unexplained objects. Burchard appeared on screen alongside Avi Loeb, both men discussing 3 Atlas and its anomalies. The pairing itself was significant. Congressional representatives don't typically share airtime with astrophysicists to discuss ongoing scientific observations. They do interviews about legislation, about policy, about political controversies. Science communication is usually left to scientists and educators, but here was a member of Congress during an active government shutdown, taking time to publicly discuss an interstellar object. Burchett spoke about the need for transparency, about ensuring the public has access to information collected by federally funded missions. He framed it as a matter of principle that NASA's data belongs to the American people who paid for it, that there's no justification for withholding observations of a natural phenomenon. The subtext was clear. Burchett believed something was being withheld, and he was using his platform to apply pressure to make it politically uncomfortable for agencies to remain silent. Then came Representative Anna Paulina Luna from Florida. Luna had been briefed apparently on the elongated Perseverance images. She reached out directly to Avi Lobo, asking for his analysis of the photograph showing the stripe. This is unusual. Members of Congress receive scientific briefings regularly, but they typically come from agency officials, from NASA scientists, from the Science and Technology Committee's designated experts. They don't usually cold call university professors for second opinions. The fact that Luna sought outside expert analysis suggests either she wasn't satisfied with official explanations or she wasn't receiving official explanations at all. Either scenario is troubling. If NASA provided briefings that didn't adequately explain the images, that implies the agency itself was uncertain or evasive. If NASA provided no briefings despite congressional interest, that suggests information was being actively restricted. Luna went further. She sent a letter to NASA's leadership advocating for the use of the Juno spacecraft, currently orbiting Jupiter, to study 3 Atlas when the comet passes relatively close to Jupiter in March 2026. The letter emphasized the scientific value, the unique opportunity, the importance of maximizing observations of interstellar objects given their rarity. But letters from representatives to agency heads about specific scientific missions are not routine. Congress sets budgets and provides oversight, but they generally don't micromanage which astronomical targets specific spacecraft should observe. That's left to mission scientists and peer review panels. Luna's letter suggested either exceptional constituent interest, which seems unlikely for an obscure astronomical event, or exceptional concern based on information that prompted her to personally intervene in mission planning. The pattern across these political engagements pointed to something. Multiple members of Congress from different committees expressing interest in 3 Atlas, White House staff being questioned about presidential briefings, scientists being invited to share platforms with politicians. This doesn't happen for typical astronomical discoveries, no matter how scientifically interesting. Consider the comparison. When the first image of a black hole was released in 2019 by the Event Horizon Telescope collaboration, it was front-page news, a scientific triumph, the culmination of decades of theoretical work and years of data analysis. But no members of Congress appeared on television to discuss it. The White House didn't issue statements. It remained a scientific story covered by science journalists, celebrated by the astronomy community, but not elevated to political discourse. Or take the discovery of phosphine in Venus's atmosphere in 2020, which briefly suggested the possibility of microbial life in the Venerian clouds. That was a bigger story in some ways, touching on astrobiology and the search for life beyond Earth. It generated excitement and debate, but again, no political involvement beyond routine NASA press releases. 3 Atlas was different, and the difference seemed to be precisely the ambiguity, the unresolved questions, the possibility that interpretations might shift based on what the data actually showed. There's a historical precedent worth considering. In 1960, When the first serious proposals for SETI emerged, the systematic searches for extraterrestrial intelligence, scientists and policymakers quietly developed protocols for what should happen if an artificial signal were detected. Those protocols emphasized verification, caution, and international coordination before public announcement. The underlying assumption was that unilateral disclosure by a single nation or institution could cause panic, could be misinterpreted, could trigger diplomatic incidents. Those protocols aren't binding treaties. They're guidelines developed through workshops and conferences, recommendations about best practices, but they reflect a consensus that intelligence is a species-level event with implications beyond science, requiring coordination at governmental levels. If observations of 3 Atlas produced data that was ambiguous enough to potentially suggest artificial origins, even as one possibility among several, it would be reasonable for federal agencies to brief elected officials, not to confirm alien technology, but to inform them of an anomalous situation where public interest was high and where data interpretation was uncertain, to prepare them for questions from constituents and media, to coordinate messaging so that different agencies weren't contradicting each other. The shutdown complicated everything. During normal operations, NASA has public affairs officers, prepared statements, coordinated communication strategies, but during a shutdown with skeletal staff, that infrastructure breaks down. Scientists furloughed can't respond to media inquiries. Press releases don't get drafted. Coordination between agencies falters, and into that vacuum, individual scientists started speaking independently. Low published blog posts daily. Other astronomers giving interviews to science journalists. Amateur researchers posting analyses on social media. Without central coordination, the narrative fragmented. Multiple interpretations circulated simultaneously. None officially endorsed, all competing for attention. From a political perspective, this was problematic. If you're trying to manage information about an ambiguous situation, the last thing you want is decentralized communication where different experts offer contradictory interpretations. It makes governance difficult. It makes it harder to maintain consistent messaging. It invites conspiracy theories because the absence of official clarity allows speculation to flourish. Some observers suggested this was deliberate, that the shutdown was timed to prevent coordinated disclosure, that by furloughing NASA staff, the administration created plausible deniability for why information wasn't being released. If scientists aren't working, if data isn't being processed, if websites aren't being updated, then of course there's silence. It's not suppression, it's logistics. But timing coincidences can be genuine. Government shutdowns happen when budget negotiations fail, driven by political factors unrelated to astronomical events. And October 1st happened to be 2 days before the Mars flyby, purely by chance. The federal fiscal year ends September 30th. Budget continuing resolutions either pass or fail based on congressional votes and presidential decisions about signing or vetoing. A comet's trajectory doesn't influence that process. Still, the coincidence gnawed at people in the same way that 7 anomalies in the trajectory and chemistry of 3 Atlas accumulated into something that felt less and less like random chance. The timing of political silence, of technological silence from multiple nations, of a shutdown that disrupted communication precisely when communication was most wanted. All of it felt orchestrated, even if it wasn't. Dr. John Brandenburg added another voice to the political dimension. A plasma physicist with experience in defense research, Brandenburg maintains a website called Blue Planet Red, where he discusses Mars research, including controversial theories about past nuclear events on Mars. He posted a video analyzing 3I Atlas, noting the White House statements, and emphasizing that official reassurances often precede more detailed disclosures. Brandenburg's track record is mixed. He's published peer-reviewed papers on plasma physics alongside speculative theories about ancient Martian civilizations that most scientists reject. He exists in that ambiguous space where legitimate credentials coexist with fringe theories. But his involvement highlighted how 3EAS was attracting attention from diverse quarters, from mainstream scientists to those who operate at the boundaries of accepted. The political interest, the questions being asked at high levels, the unusual coordination required to explain the silence across multiple nations, all of it suggested that 3 Atlas had become more than an astronomical curiosity. It had become an event requiring management, requiring decisions about what to say and when to say it, requiring briefings and coordination that go beyond typical scientific discovery. And that management, that careful control of information, couldn't last forever. Eventually, observations would be processed, papers would be published, data would emerge into the public domain through peer review or through leaks. The questions would demand answers, and those answers, when they came, would have to address not just what 3 Atlas is, but why the response to it required political involvement at all. Meanwhile, amateur astronomers weren't waiting for official channels. They had their own telescopes, their own processing software, their own communities for sharing and analyzing data. And in the absence of professional releases, amateur observations became the primary source of visual information about 3 Atlas. Some of those observations raised new questions. Some appeared to show things that shouldn't be there, and some were almost certainly imaging artifacts, misinterpretations, or wishful thinking. But separating signal from noise when everyone's looking at faint objects through atmospheres with modest equipment that becomes nearly impossible without professional resources to provide ground truth. Chapter 8. The amateur images NASA doesn't want you to see. Amateur astronomy has a rich history of contributing to professional science. Supernova discoveries, comet findings, variable star monitoring. All these efforts rely partly on networks of amateur observers with backyard telescopes and dedication to watching the night sky. There are thousands of amateur astronomers worldwide with equipment that would have been considered professional grade just a generation ago. CCD cameras, computerized mounts, sophisticated image processing software. The barrier between amateur and professional capabilities has blurred considerably. When 3 Atlas was discovered, amateur astronomers immediately began tracking it. Coordinates were posted online. Ephemerides, tables predicting where the object would appear each night, were calculated and shared. Observing campaigns were organized through forums and social media groups. People wanted to see this interstellar visitor for themselves, to capture their own photons that had bounced off something from beyond our solar system. One of those observers went by the username Dobsonian Power, named after Dobsonian telescopes, a popular design among amateurs for its simplicity and large aperture. On October 3rd, as 3 Atlas made its closest approach to Mars, Dobsonian Power was observing from his location with a solar telescope, equipment designed to safely observe the sun by blocking most of its light while allowing specific wavelengths through. Why use a solar telescope to observe a comet? Because 3 Atlas was in the sky near the sun from Earth's perspective, not directly in front of it, but close enough that observing during daylight with specialized equipment became necessary. Solar telescopes with narrowband filters can detect bright objects near the sun that would be invisible to normal telescopes, washed out by solar glare. Dobsonian Power captured an image and posted it online. The image was heavily processed, enhanced to bring out faint features with contrast pushed to maximum. What appeared was controversial. A dark, somewhat elongated feature against a lighter background. Grainy, unclear, but undeniably showing structure of some kind. Within hours, the image went viral. Comment sections exploded with interpretations. Some saw clear evidence of an elongated object, vindication of the Perseverance images. Others saw nothing but noise, artifacts of aggressive image processing, pareidolia, the human tendency to see patterns in random data. A few pointed out that solar telescopes aren't designed for observing comets, and that the optics could introduce distortions. Professional astronomers were quick to express skepticism. The image quality was poor, the processing was excessive. Without knowing the exact equipment parameters, exposure times, and processing steps, it was impossible to evaluate what was real signal and what was artifact. One astronomer noted that when you enhance images aggressively enough, you can make anything appear to have structure. Noise patterns become features. Optical aberrations look like edges. The human brain does the rest, connecting dots into shapes. But the image's technical shortcomings didn't prevent it from spreading. News outlets picked it up. YouTube videos analyzed it. Comparisons were made to the Perseverance images, to earlier Hubble photos, to artist renderings of what an interstellar probe might look like. And inevitably, AI-generated images began appearing, purporting to show what 3 Atlas really looked like. Sleek metallic structures with impossible detail, completely fabricated, but presented as enhanced versions or artist interpretations. The flood of AI-generated content created a secondary problem. How do you distinguish real amateur observations? Flawed but genuine attempts to image the object from fictional renderings designed to generate clicks. Some AI images were obviously fake, showing surface details no telescope could resolve at those distances. But others were more subtle, showing plausible comet-like structures with just enough ambiguity to seem like they could be real photographs. Meanwhile, legitimate amateur observations continued. Astrophotographers with tracking mounts, telescopes that automatically compensate for Earth's rotation to keep targets centered during long exposures, were capturing better quality images than Dobsonian P's solar telescope attempt. Gerald Raymond and Michael Jagger in Namibia had already captured the green color change. Other observers in the southern hemisphere, where 3 Atlas was better positioned before it swung behind the sun, were uploading their results to astronomy forums. These images showed something interesting. When properly tracked and imaged with narrowband filters that isolated specific emission lines, 3 Atlas appeared to have an extended white or yellow core surrounded by a green halo. The core looked elongated in many of the better images, not dramatically so, but noticeably non-circular. The elongation wasn't 4:1 like the Perseverance composite, but more like 2:1 or 1.5:1. Was this real structure, or still an artifact? Tracking telescopes compensate for Earth's rotation, but the comet itself is moving against the background stars. If exposure times are long enough, that motion can blur the image, potentially creating elongation in the direction of motion. But some exposures were short, under a minute, not long enough for significant smearing. And the elongation appeared consistent across different observers with different equipment in different locations. One observer, posting under the name Red Collie and identified as Dr. Horace Drew, had been particularly vocal about the color distribution. Drew posted enhanced versions of multiple amateur images showing the white center and green periphery. His argument remained that if the object were a small spherical nucleus surrounded by a large green coma, and you're looking at it through a telescope that smears the image slightly due to atmospheric turbulence and instrument limits, you should see a predominantly green blur. The white shouldn't dominate the center unless the white emitting region is larger than the green emitting region. Professional astronomers countered that comas are not uniformly bright. They're densest near the nucleus and fade with distance. If you have a bright nucleus surrounded by a fainter coma, even if the coma is green and extensive, the central brightness from the nucleus will dominate in images unless exposures are specifically calibrated to bring out faint, extended emission. Most amateur images are optimized to capture the bright core, not the faint outer coma. So seeing white centers isn't surprising. The back and forth between Drew and other observers highlighted a fundamental challenge. Interpreting astronomical images requires understanding the imaging process, the instrument response, the exposure settings, the processing applied. Two people looking at the same raw data can produce different processed images that emphasize different features. And without agreed-upon standards for how processing should be done, arguments about what images actually show become subjective. Amateur images also suffered from a signal-to-noise problem. 3 Atlas was never bright. At its peak, it reached around magnitude 8 or 9, too faint to see with the naked eye, but visible through binoculars or small telescopes under dark skies. Most amateur equipment has limited sensitivity. Capturing a clear image requires long exposures, stacking multiple frames, careful processing. Each step introduces opportunities for artifacts. Professional observatories have larger mirrors, better cameras, darker skies, decades of experience calibrating instruments. They know their telescope's quirks, how to correct for optical aberrations, how to flat field images to remove uneven sensitivity across the detector, how to subtract background sky glow. Amateur observers often lack that expertise or equipment. Their images are valuable for detection and rough characterization, but not for detailed analysis of subtle structural features. Yet, in the absence of professional images from Mars orbiters, amateur observations were all the public had, and that created a vacuum where speculation could thrive unchecked. If NASA or ESA had released even preliminary high-resolution images, even raw, uncalibrated frames, it would have anchored the conversation in reality. People could debate what the professional images showed, but at least the debate would be grounded in high-quality data. Instead, the conversation centered on heavily processed amateur images of varying quality, supplemented by AI-generated fakes filtered through social media algorithms that prioritized engagement over accuracy. The loudest voices weren't necessarily the most informed. The most sensational interpretations got the most shares, and the truth, whatever it was, became harder to extract from the noise. Some observers tried to inject sanity. They posted tutorials on astrophotography, explaining common artifacts, demonstrating how processing choices affect final images. They showed how easy it is to create false structures through over-sharpening, how cosmic ray hits on camera sensors can look like stars or anomalies, how diffraction spikes from telescope supports can be mistaken for real features, but nuance doesn't go viral. Careful explanations get fewer views than bold claims, and when people want to believe something extraordinary is happening, they're selective about which expert opinions they trust. Skeptical astronomers become part of the cover-up. Enthusiastic interpreters become truth-tellers. The normal quality control mechanisms of science, peer review, and replication don't function well on social media, where anyone can post anything, and algorithms amplify whatever generates clicks. A website appeared dedicated to collecting and analyzing all available images of 3I Atlas. The site, run by someone calling themselves an independent researcher, compiled amateur observations, professional press releases, scientific papers, and blog posts. But it also gave equal weight to unsupported speculation and carefully vetted data. A graph showing nickel emission rates from the Very Large Telescope appeared alongside AI-generated images of hypothetical spacecraft. The mixing of reliable and unreliable sources created an environment where distinguishing truth from fiction required expertise most visitors didn't have. As October wore on and 3I Atlas moved closer to the Sun, Earth-based observations became impossible. The angular separation from the Sun decreased below the threshold where even specialized equipment could safely observe. By mid-October, the comet was lost in solar glare from our perspective. It would remain invisible until early December, when it emerged on the far side of the Sun, by which time perihelion would have passed, and the most intense activity would be over. That meant the amateur observation campaign ended just when things were getting most interesting. The final images captured before solar conjunction showed 3I Atlas brightening, the coma expanding, the green glow intensifying, all consistent with a comet approaching perihelion and outgassing more vigorously as solar heating increased. Nothing in those final amateur images definitively resolved the debates about structural composition. They showed an active comet, bright and fuzzy, moving through the sky as expected. But the absence of continued Earth-based observation meant that whatever happened at perihelion would only be witnessed by spacecraft. The Solar and Heliospheric Observatory SOHO, orbiting at the L1 Lagrange point between Earth and Sun, had instruments that could observe the region near the Sun. The Parker Solar Probe, on its close passes around the Sun, might catch glimpses. ESA's JWST spacecraft, en route to Jupiter, but with a vantage point outside Earth's orbit, was planning observations in November. Those observations would be critical. They would capture 3I Atlas at its most active state, when solar energy was maximal, when outgassing would peak, when any unusual behaviors would be most evident. If the object was going to do something unexpected, if it was going to fragment or maneuver or exhibit any characteristic that deviated from normal cometry physics, perihelion was when it would happen. October the 29th loomed as the moment of truth, the day when 3 Atlas would pass 1.36 astronomical units from the Sun, just inside Mars' orbit, closer to our star than it had ever been in its billions of years of wandering through interstellar space, closer than its formation, around whatever star system it came from. Assuming that system star was similar to or cooler than our Sun, what would happen when gigawatts of solar energy poured onto its surface? Would it survive intact, or would thermal stresses crack the nucleus into fragments? Would outgassing increase predictably, following thermal models, or would the steep power law relationships in nickel and cyanide production extrapolate to even more extreme rates? Would the object continue on its hyperbolic trajectory unchanged, or would any non-gravitational forces from asymmetric outgassing alter its path measurably? And underneath all those scientific questions was a deeper one that nobody wanted to voice too loudly, but that lingered in every discussion. If 3I Atlas was artificial, if some of the anomalies pointed to technology rather than geology, would perihelion be a scheduled event, an activation point, a moment when solar energy charged systems that had been dormant during billions of years in the cold of interstellar space? Would something that looked like a comet under distant observation reveal itself to be something else when subjected to maximum solar input? The speculation was uncomfortable for scientists. It ventured into territory where data thinned and imagination filled gaps. But October the 29th was coming, and when it arrived, someone somewhere would be watching. Chapter 9. October the 29th. The moment of truth. Perihelion is not merely a point on an orbit, it's a crucible. For comets, it represents maximum stress, maximum energy input, maximum activity. The physics is straightforward. Solar radiation follows an inverse square law. At 1 astronomical unit from the Sun, Earth's distance, the solar constant is about 1,360 watts per square meter. Move to 1.36 astronomical units, where 3I Atlas would reach perihelion, and that drops to about 730 watts per square meter, still substantial, still enough to drive powerful chemistry. For an object that had spent billions of years in the cold of interstellar space, where temperatures hover just degrees above absolute zero, where sunlight is imperceptible, this represented a shock. Even during its journey through our solar system from beyond Jupiter's orbit inward, 3I Atlas had never experienced this intensity. And if the steep power laws governing its nickel and cyanide production held, if those relationships extrapolated forward, then perihelion should trigger an eruption of outgassing that would dwarf anything observed earlier. The Solar and Heliospheric Observatory, SOHO, has been watching the Sun continuously since 1995. Positioned at the L1 Lagrange point, about 1.5 million kilometers from Earth toward the Sun, SOHO maintains a permanent view of the solar disk and the space immediately around it. Its LASCO coronagraphs block the Sun's direct light to observe the faint corona and to detect objects passing near the Sun. SOHO has discovered thousands of comets, most of them small sun-grazing comets that plunge close to the solar surface and often disintegrate. The spacecraft wasn't designed to study interstellar objects, but its position and instruments made it capable of observing 3I Atlas as it passed through the inner solar system. Parker Solar Probe presented another opportunity. This NASA mission, launched in 2018, is designed to fly closer to the Sun than any previous spacecraft, studying the solar corona and solar wind from inside the orbit of Mercury. Its perihelion passes take it to within 6 million kilometers of the solar surface, close enough that the spacecraft requires a specialized heat shield to survive temperatures exceeding 1,000 degrees Celsius. Parker wasn't going to be at perihelion simultaneously with 3 Atlas. The spacecraft follows its own elliptical orbit, and timing didn't align. But Parker's WHISPER instrument, the Wide Field Imager for Solar Probe, has a field of view that can capture objects in the inner solar system. Mission planners calculated that between late September and early November, WHISPER should be able to observe 3I Atlas, at least peripherally, depending on exact positions and pointing schedules. The challenge with both SOHO and Parker observations is that they're designed for solar physics, not for detailed cometry studies. SOHO's coronagraphs have relatively coarse spatial resolution. They can detect the presence of a comet, measure its approximate brightness, track its path, but they can't resolve structure at the level needed to distinguish a compact nucleus from an extended coma, much less determine shape or detect surface features. Parker's WHISPER has better resolution, but was optimized for imaging the solar wind, not solid objects. And Parker's trajectory meant any observations of 3I Atlas would be from unfavorable angles, catching the comet in the background of solar observations rather than as a primary target. The spacecraft that could have provided the best perihelion observations was ESA's JWST, the Jupiter Icy Moons Explorer. JWST launched in April 2023 and was en route to Jupiter on a trajectory that happened to place it in an excellent position to observe 3I Atlas in November, about 2 weeks after perihelion. At that point, the comet would still be highly active, close enough to the Sun that outgassing would continue at elevated rates, but far enough that JWST's instruments wouldn't be overwhelmed by solar glare. JWST carries multiple cameras and spectrometers designed to study icy moons. Those same instruments are perfectly suited for observing a comet. The Janus camera system can capture color images with resolution good enough to see structural details. The MAGIS spectrometer can analyze the chemical composition of the coma across visible and infrared wavelengths. The UVS ultraviolet spectrograph can detect gases that emit in UV. ESA confirmed that JWST would observe 3I Atlas starting November the 2nd and continuing through late November. They emphasized that this would provide the best views of the comet in its most active state, when the tail would be fully developed and the brightness would peak. But JWST observations would come after perihelion. Whatever happened at the moment of closest approach, during those hours when solar heating reached its maximum, would occur when no spacecraft had an optimal view. SOHO might catch glimpses, Parker might capture distant images, but the detailed, high-resolution observations that could definitively answer questions about structure, about the nuclear size and shape, about whether outgassing was symmetric or asymmetric, those observations wouldn't exist for the perihelion moment itself. Ground-based astronomers were completely blind. 3I Atlas remained on the far side of the Sun from Earth's perspective, hidden behind 147 million kilometers of incandescent plasma. No telescope on Earth or in Earth orbit could observe it. The geometry simply didn't allow it. This observational gap was frustrating for scientists who wanted to understand perihelion behavior, but it also created a peculiar situation for those who suspected 3I Atlas might be artificial. If something were going to happen, if a maneuver were planned, or if systems were going to activate, the moment of maximum solar energy input, while hidden from Earth's direct view, would be an optimal time. Some had noted this back in July when the trajectory was first calculated. Avi Loeb mentioned it in one of his papers, pointing out that 3 Atlas would be occulted by the Sun from Earth's perspective during its perihelion passage. If you wanted to conduct operations without being observed by one particular planet, arranging perihelion to occur when that planet can't see you would be clever. Of course, this assumes the trajectory was designed, which remains purely speculative. Natural orbits don't care about observational geometry from Earth. The fact that perihelion happens to occur when Earth can't watch is simply chance, a consequence of when 3I Atlas entered the solar system and what trajectory it followed. Reading intent into it requires believing the entire journey was planned, which is a leap unsupported by evidence. But the speculation existed. Online forums discussed it extensively. What if 3I Atlas used a solar Oort maneuver? The Oort effect is a real phenomenon in orbital mechanics. If you have a propulsion system and you fire it when you're deep in a gravity well, moving at high velocity, you get more change in kinetic energy than if you fire the same propulsion system in deep space. It's most efficient to do burns at perihelion. If 3I Atlas wanted to change its trajectory to go from a hyperbolic escape path to a bound orbit that would keep it in the solar system, the best place to do that maneuver would be at perihelion. You'd get maximum efficiency from your propulsion, whatever form it took. And if you timed it so Earth couldn't directly observe the maneuver, you'd have plausible deniability. By the time you came around the Sun and Earth could see you again in December, the maneuver would be complete. You'd be on a new trajectory, but observers would need time to calculate your new orbit and realize it had changed. This is science fiction territory. Actual evidence for deliberate maneuvering was absent, but the scenario was physically plausible, and that made it compelling to some. The natural expectation for perihelion was also dramatic. If 3 Atlas was a comet, and if the steep power law relationships in nickel and cyanide production continued, then perihelion should produce a massive outburst. The production rates had increased 25-fold from late July to late August. Extrapolating that curve forward to perihelion suggested production rates could increase by another factor of 10 or more. That level of outgassing could alter the comet's appearance significantly. The coma would expand, potentially growing to encompass hundreds of thousands of kilometers. The tail, which had been faint and short in earlier observations, would stretch out dramatically as solar wind and radiation pressure pushed dust and gas away from the nucleus. The brightness would increase, possibly making the comet visible to the naked eye if it weren't hidden behind the sun. Thermal stress could also fragment the nucleus. Many comets break apart at perihelion when heating causes internal pressure to build up faster than it can be released through surface venting. If 3I Atlas had structural weaknesses, if its nucleus was a loose aggregate of smaller pieces held together weakly, perihelion stress could split it. Fragmentation events are spectacular. The nucleus breaks into 2 or more pieces, each developing its own coma. The brightening can be dramatic as fresh, icy surfaces get exposed to sunlight. But fragmentation also marks the beginning of the end for a comet. The pieces disperse over subsequent orbits. Their total surface area increases, and they sublimate away faster than they would have as a single body. Fragmentation is a death sentence for comets, just slower than immediate disintegration. Would 3I Atlas survive perihelion intact? The answer would tell us something about its structure. A coherent solid nucleus, whether rocky or icy, should survive. A rubble pile might not, and if it was artificial, if it had internal structure that provided strength beyond what random aggregation would give, that would show in its survival. The waiting was difficult. October the 29th arrived. The day passed. 3I Atlas swept through perihelion while Earth remained oblivious, facing the wrong direction, the sun itself blocking the view. Spacecraft collected what data they could from their distant or oblique vantage points. Somewhere in the inner solar system, hidden from our eyes, something was happening to an object that had traveled for billions of years to reach this moment. Solar heating vaporized ices. Pressure built within the nucleus as gases expanded. Material streamed away into space, propelled by sublimation, by thermal expansion, by the relentless push of solar radiation. Nickel atoms, if the power laws held, were being released at unprecedented rates, glowing green as they fluoresced under UV bombardment. Cyanide radicals formed and dissociated in complex chemical cascades. Dust grains lifted off the surface, carried by escaping gases, catching sunlight and reflecting it back into space. And then, perihelion passed. 3 Atlas began its outbound journey. The distance from the sun started increasing. Solar energy input began declining. The furious activity of perihelion would gradually subside as the comet moved back toward the cold of the outer solar system. But it would take time for observations to reach Earth. SOHO data would be downlinked and processed. Parker observations would be analyzed. The spacecraft couldn't transmit everything in real time. Data had to be stored, compressed, sent back to Earth through the Deep Space Network's radio telescopes, received and decoded. Then scientists would need time to interpret what they were seeing. Early November would bring the first perihelion observations. The JWST spacecraft would get its views in the second week of November, and finally, in early December, 3 Atlas would emerge from behind the sun from Earth's perspective. Ground-based telescopes could resume observations. The comet's post-perihelion appearance, its brightness, its spectral characteristics, its trajectory, all of that would be measured carefully. If it looked like a normal comet after perihelion, active but following predictable patterns, that would be one answer. If it had fragmented, that would suggest internal weakness, a natural structure unable to withstand thermal stress. If it looked different, if its chemistry changed, if its trajectory showed unexpected deviations, that would raise new questions. The wait for December felt interminable. Weeks of uncertainty, of relying on incomplete data from spacecraft not designed for this task, of watching internet speculation spiral while concrete information remained scarce. Scientists tried to manage expectations. They reminded the public that data takes time to process, that preliminary results can be misleading, that patience is required for good science. But patience is hard when the stakes feel high, when an interstellar object might be the most important astronomical discovery of the century, or might be nothing unusual at all, when the answer might redefine humanity's place in the universe, or might simply add another data point to our catalog of comets. October the 29th came and went. The perihelion moment passed into history, and 3 Atlas, whatever it truly was, continued its journey through space, carrying its secrets with it into the darkness beyond the sun, waiting to be seen again when Earth's orbit brought us back into alignment, waiting to reveal whether it survived, whether it changed, whether the moment of maximum solar input had triggered anything unexpected, waiting to answer, if only partially, the questions that had accumulated across months of observation and debate. Chapter 10. What happens if we're wrong? There's a thought experiment that philosophers and scientists sometimes pose when discussing existential risks. Imagine you're given a sealed box and told there's a 10% chance it contains something that will end human civilization, but a 90% chance it's harmless. Do you open it? Most people say no. The asymmetry of outcomes makes caution rational. A 10% risk of catastrophe outweighs a 90% probability of nothing. Now modify the experiment. The box is opening automatically in 1 month. You can't stop it. You can study it externally, run tests, gather information that might help you prepare for what's inside. Do you look? Do you measure? Do you try to understand, even though understanding might be unsettling? That's roughly where humanity finds itself with 3 Atlas. The object is here, moving through our solar system on a path we can't alter. It will exit eventually, continuing its journey through interstellar space. We can observe it or ignore it. We can gather data or remain deliberately ignorant, but we can't make it go away. The Trojan horse analogy that Avi Loeb invoked has historical weight. Around 1200 BCE, according to legend, the Greeks besieged Troy for 10 years without success. Then they built a giant wooden horse, left it outside the city gates as an apparent offering, and sailed away. The Trojans, believing they'd won, brought the horse inside. That night, Greek soldiers hidden within the horse emerged and opened the gates for their returning army. Troy fell because they welcomed something they didn't understand. If 3I Atlas is artificial, if some fraction of its observed properties genuinely indicate technology rather than geology, then its purpose is unknown. The default assumption, the optimistic scenario, is scientific curiosity. An advanced civilization sends probes to explore, to gather data, to learn about other star systems, much as we've sent Voyager and Pioneer probes out of our own solar system. Peaceful exploration, no hostile intent. But that assumption is just that, an assumption. We have no way to verify intentions. An object that appears to be a comet, but is actually a probe, could be gathering intelligence about our solar system, about Earth, about whether life exists here. It could be reporting back, transmitting data via methods we can't detect, or on timescales too slow for us to notice during its brief passage through. Or it could be more directly concerning. The paper that Loeb co-authored with Adam Hibbert and Adam Crowell, titled, "Is the Interstellar Object 3I Atlas Alien Technology?" explored scenarios where the trajectory and timing weren't coincidental, where the close approaches to Mars, Venus, and Jupiter served purposes beyond random chance, where perihelion behind the sun allowed for maneuvers or activities that Earth couldn't observe. The paper was careful to label itself a pedagogical exercise, an exploration of possibilities rather than a claim of probabilities, but it outlined scenarios that were unsettling. If a civilization wanted to conduct reconnaissance of our solar system, 3I Atlas's trajectory would be nearly optimal. Retrograde orbits are harder to intercept. Close passes of multiple planets allow for gravitational assists to alter the trajectory, or for deployment of smaller probes that could even break into planetary atmospheres. The paper calculated that if 3I Atlas used a reverse solar Oort maneuver at perihelion, it could potentially change from an escape trajectory to a bound orbit, remaining in the solar system indefinitely. The optimal timing for such a maneuver would be when Earth couldn't observe it, which happened to be exactly when perihelion occurred. Is this what happened? There's no evidence yet. Trajectory calculations require precise position measurements over time. Until 3I Atlas emerges from solar conjunction in December and can be observed again, astronomers can't definitively determine if its path changed. And even if the trajectory did change, non-gravitational forces from asymmetric outgassing could explain it. Comets routinely experience small trajectory changes from outgassing jets that produce thrust. Distinguishing a natural trajectory change from an artificial one requires detailed observations of where the outgassing occurs, how symmetric it is, whether the forces produced align with observable jets. That level of analysis takes time and high-quality data. But the scenario raises uncomfortable questions. If an interstellar probe wanted to remain in our solar system, perhaps to continue observations over decades or centuries, how would we stop it? The answer is, we couldn't. Our fastest spacecraft travel at a few dozen kilometers per second. 3I Atlas moves at over 60 kilometers per second relative to the Sun. We have no way to intercept something moving that fast. No propulsion system that could match its velocity. No weapons that could reach it. Even if we detected clear evidence of artificial origin, even if we knew with certainty that 3I Atlas was technology from another civilization, our response options would be limited to watching and worrying. We could point more telescopes at it. We could attempt radio communication, though the round-trip light time to an object at several astronomical units would make conversation impossible. We could alert international authorities, convene emergency sessions at the United Nations, coordinate scientific responses. But in terms of actual defensive measures, we have none. If the probe's intentions were hostile, if it was designed to assess our capabilities before some future action, we'd be powerless to prevent whatever comes next. This is why some argue against aggressive observation. If we're being studied, if our radio and television signals have already announced our presence, does pointing telescopes at an interstellar visitor change anything? Or does it simply confirm that we've noticed that we're paying attention, potentially triggering responses we can't predict? Others argue the opposite. Ignorance isn't safety. If something potentially technological is passing through our solar system, gathering as much information as possible is essential. Understanding its capabilities, its composition, its behavior. That knowledge could be crucial if more such objects arrive in the future. We can't defend against what we don't understand, but we might be able to prepare if we learn enough. The philosophical implications extend beyond immediate security. Confirmation that 3I Atlas is artificial would mean we're not alone. Not in the abstract sense of believing life probably exists elsewhere in the universe, but in the concrete sense of knowing that another technological civilization exists and has the capability to send objects across interstellar space. That knowledge would fundamentally alter human self-perception. We'd no longer be unique. Our achievements in science, technology, art, philosophy, all would need to be contextualized against the existence of others who've likely achieved more, given they've mastered interstellar travel while we've barely reached our own moon. Some might find that humbling in a positive way, a reminder of our small place in a vast universe, an incentive to mature as a species, to overcome our divisions and conflicts. Others might find it threatening. If we're not alone, if we're potentially being observed or assessed, then our future might not be entirely in our own hands. The societal impacts would ripple through institutions. Religions would need to reconcile their theologies with extraterrestrial intelligence. Governments would face questions about why they didn't prepare, why they didn't take the possibility seriously. Scientists would shift priorities toward understanding the implications, toward figuring out if communication is possible, or if we should remain silent. Economic impacts might be subtle but significant. If technology vastly beyond ours exists, it changes the calculus of long-term investment. Do we continue developing certain technologies, knowing they might become obsolete if we ever gain access to alien knowledge? Or do we accelerate research, trying to advance as quickly as possible to narrow the gap? Military strategies would require complete rethinking. If potential adversaries exist with capabilities we can barely imagine, then Earth's geopolitical conflicts become almost meaningless. You don't worry about territorial disputes with neighboring countries when there might be interstellar powers monitoring your planet. But all of this assumes 3I Atlas is artificial, and the probability, most scientists would argue, remains low. The anomalies are real. The observations are puzzling, but natural explanations, however strained, are still more likely than artificial ones, simply because we have no prior evidence that interstellar probes exist. The cost of being wrong, though, is asymmetric. If we assume it's natural and we're wrong, we miss an opportunity to learn, to communicate, to prepare. We might remain ignorant of a presence in our solar system until it acts in ways we can't ignore. If we treat it as potentially artificial, and we're wrong, we've expended extra observational resources, published some incorrect papers, and looked foolish to future historians. The cost of treating it as natural when it's artificial is potentially much higher than the cost of treating it as artificial when it's natural. This asymmetry justifies extra caution, extra observation, extra analysis. It justifies taking the possibility seriously, even if the probability seems low. In early December, when 3I Atlas becomes visible from Earth again, when telescopes can resume observations and calculate its post-perihelion trajectory, we'll have new data. If it fragmented, that strongly suggests a natural origin. Artificial probes don't usually break apart from thermal stress. If its trajectory shows no unexpected changes, that increases the likelihood it's a comet following purely gravitational and outgassing influence motion. If its chemistry remains bizarre, if the nickel emission continues, if the color and structure raise more questions than they answer, then the debate will continue. And this is the scenario that keeps some scientists awake at night, if the trajectory shows changes inconsistent with natural outgassing, if the object has maneuvered in ways that require acknowledging deliberate thrust, then everything changes. The Galileo project, which Lowe directs, was founded to investigate potential evidence of extraterrestrial technology, both historical through studying interstellar objects and current through monitoring for unidentified aerial phenomena. The project operates 3 observatory sites with instruments designed to detect and characterize anomalous objects. If 3I Atlas does something unexpected When it emerges from solar conjunction, Galileo Project telescopes will be watching. So will dozens of professional observatories worldwide. So will thousands of amateur astronomers with their backyard equipment and their dedication to understanding the cosmos. The observational campaign for 3I Atlas's reappearance will be one of the most coordinated efforts in astronomical history, driven not just by scientific curiosity, but by the nagging possibility that this object might be more than it appears. Between now and December, the waiting continues. Data from perihelion slowly trickles in. Scientists analyze SOHO observations frame by frame, looking for anything unusual in the comet's appearance or behavior during closest approach. The JWST spacecraft prepares its instruments for November observations. Mission planners calculating optimal pointing angles to maximize data quality. And people wonder in online forums and coffee shops, in university lecture halls and government briefings. The question persists. What is 3I Atlas? Rock or probe? Ancient comet or ancient technology? Natural wanderer or designed explorer? The answer, when it comes, might not be definitive. Science rarely delivers absolute certainty, especially about objects we can only observe from a distance with limited data. But the search for that answer, the process of gathering evidence and evaluating possibilities, that process continues because understanding what passes through our solar system, understanding whether we're alone or observed, understanding the nature of interstellar visitors, these questions touch on the deepest aspects of human curiosity and our place in the cosmos. December approaches, the comet moves through space, and we wait to see what emerges from behind the sun. And so we find ourselves here at this peculiar moment in human history, watching the sky with instruments our ancestors could never have imagined, searching for answers to questions that transcend science and touch something deeper. 3I Atlas continues its journey, indifferent to our debates, our fears, our hopes. It moves through the darkness beyond the sun, carrying whatever truth it holds, waiting to be seen again when the geometry of orbits brings us back into alignment. We've traced the evidence together. The elongated photos from Mars that sparked a debate still unresolved. The coordinated silence from space agencies across the globe. Rivals united in their reluctance to share. The green glow that appeared without the molecules that should cause it. The nickel streaming into space at rates that defy simple explanation. The 7 statistical improbabilities that accumulate like evidence in a trial where the verdict remains undecided. The political whispers at levels where decisions about disclosure are made. The amateur astronomers filling the void with images of varying quality and interpretation. And the perihelion passage hidden from our eyes where solar energy poured onto a surface that had known only the cold of interstellar space for billions of years. 2 options remain: an elongated object or a camera trick, an ancient comet with chemistry we've never encountered, or something that merely resembles a comet while being fundamentally different, natural or designed, random or intentional. Perhaps December will bring clarity. Perhaps the post-perihelion observations will show fragmentation, chemical changes, trajectory deviations that finally tip the scales toward one interpretation or the other. Or perhaps the ambiguity will persist, and we'll add 3I Atlas to that growing collection of cosmic mysteries where evidence points in multiple directions and certainty remains elusive. What we know for certain is this: something from beyond our solar system passed through, something old beyond our comprehension, carrying materials formed around another star, shaped by processes billions of years removed from our experience. Whether it's a messenger or a coincidence, whether it bears information or merely reflects sunlight, It reminds us that the universe is larger and stranger than our daily lives allow us to remember. Thank you for spending these hours with me exploring the evidence and the implications of this remarkable visitor. If you found this journey worthwhile, I'd be grateful if you'd consider liking this video and subscribing to the channel. It helps more people discover these stories, and it supports the creation of more deep dives into the mysteries that surround us. The content presented here is based on publicly available data, published research, and documented observations as of October 2025. Scientific understanding evolves as new evidence emerges, and interpretations that seem reasonable today may be revised or refuted by future discoveries. This video explores possibilities and presents multiple perspectives, but it makes no definitive claims about matters that remain under investigation. Always seek multiple sources, remain skeptical, and remember that the most honest answer to many questions about 3I Atlas is still, we don't know. The night sky continues its ancient rotation above us. Stars trace their paths. Planets wander against the background of constellations. And somewhere out there, beyond the sun's glare, an interstellar visitor continues its passage through our cosmic neighborhood, holding its secrets, waiting to reveal whether the strange photos from Mars showed us something profound or merely taught us about the limits of perception. Rest well and keep watching the skies. Good night.